Hello guys, welcome back. This is lecture 17 of the lecture series Signals and Systems. In this video, we'll be learning about the response of LTI systems to complex exponential, Fourier series representation of discrete time periodic signals, and we'll see the properties of discrete time Fourier series. So let's get started. So in the previous lecture, we saw about the representation of discrete time signals in terms of impulses, right? And we saw the convolution sum. So we have x of n convolved with h of n, which gives us summation k equal to minus infinity to infinity x of k h of n minus k. So what did we actually do? This is useful for LTI systems, right? So initially we represented x of n itself in the form of sum of weighted shifted impulses, right? So x of k delta of n minus k. So we represented discrete time signals as a linear combination of some basic signals, which here is the delta function, right? Delta of n minus k here. And then what did we do? We found the response of the basic signals to the LTI system, and we can easily represent the output of a signal as a linear combination of the output of basic signals, which is nothing but the h of n minus k, which we called as the impulse response, right? So this we saw it with the delta function or the unit impulse function. Now we'll see it with the complex exponential. So that is what we are going to see, response of LTI systems to complex exponentials. And why complex exponentials? Because we will finally get a way to represent basic signals or periodic signals in form of sum of complex exponentials. So that way we are again going through these two steps only, okay, to simplify our analysis of LTI systems to complex exponentials. So let us take a complex exponential. Let's say x of n equal to z power n, and z is a complex number. So now let us pass it through a LTI system with impulse response h of n. So we have z power n and we have y of n. So we know that y of n is given by x of n convolved with h of n, which is nothing but summation k equal to minus infinity to infinity. I can write it as x of k into h of n minus k, or h of k into x of n minus k. So this will be convenient for me, so I am writing it this way. So we'll see that in a minute why it is so. So then I substitute my x of n minus k, which is nothing but z power n minus k. So the summation only involves k terms. I can take z power n outside. So I will have z power n summation k equal to minus infinity to infinity h of k z of z power minus k. So I can represent this as some h of z, since it is depending only on z, and anyway k will take this h of k and minus k in the summation, it will go off. So I'll only be left with h of z. So then I can write my y of n as h of z into z power n. So what does it look like? We had the LTI system with impulse response h of n, and we had z power n, and we got the output as h of z into z power n. So you can see input being z power n and output is some multiple of z power n, right? So z power n is a eigen function of LTI systems. Of course, this h of z will change depending on the LTI system and its system response, but for a fixed LTI system, this is going to be constant, and we can say that this z power n is or the complex exponential is a eigen function of LTI system. So now if we have a system, let's say like this, z1 power n, let's say a1 z1 power n plus a2 z2 power n, then what will be the output? It will be h of z1 a1 z1 power n plus h of z2 a2 z power n, and this h of z will depend on the system response, right? Impulse response of the system. Okay, so now similarly, if I'm able to represent x of n as some summation, linear combination of this z, right? Let me call it z case. Okay, so a k z k and sum over k. Then my output will also be of similar form, only the coefficient is going to get modified a little. So it will be h of zk a k z power k power n. Okay, so this we get as a simple response, correct? So it is very easy to analyze LTI system when we can represent inputs in the form of sum of or linear combination of complex exponentials. So what will be our next goal then? To actually find this form of expression. So any given signal, we should be able to write it in the form of sum of complex exponential. Then it makes our analysis easier, right? So then that is what is called as the Fourier series representation of discrete time periodic signals. So first we look at periodic signals. Why? Because your complex exponential itself is periodic. You can have e power j omega naught n, which is periodic signal, and then you can represent your x of n in terms of sum of e power j omega naught n, and then we'll see how we can find the coefficients ak. Okay. So periodic signals, we know that your x of n is equal to x of n plus n. So your period is n here, right? So let's say it is the fundamental period. And what will be your fundamental frequency? So it will be 2 pi over n, and it is represented by omega naught. So let us analyze the complex exponential e power j omega naught n. Okay, let's say this is some x bar of n is this signal. So it can be written as e power j 2 pi by n into n. So you can observe that e power j 2 pi by n into n plus n is nothing but e power j 2 pi n by n plus 2 pi. So you know that this complex exponential is going to be periodic with period 2 pi. So this is again equal to e power j 2 pi n over n. So what are the other signals which are having the period of n? So if I have 2 omega naught, which will be given as 2 into 2 pi over n, then that will also be periodic with period n. It will not be the fundamental period, but it is still periodic with n, right? Similarly, if you have 3 omega naught, it is again periodic with n. right? And so on. And up to what point? So if I have n omega naught, then it will be 2 pi over n into n, right? And again, this is periodic with n. And we also have our constant signal 0, right? So 0 into 2 pi over n. And it is anyway going to be periodic for any n, right? It is periodic with n equal to 1. So it can be used to vary our DC part, right? But if you observe these both, so if I have e power j 0 omega naught n, it's nothing but 1, and e power j n into 2 pi over n into n, this is nothing but e power j 2 pi n, and n is an integer, so this is also going to be equal to 1, right? So these two signals are not distinct, correct? They are not distinct, because for all the n values this is going to be equal to 1 and this also equal to 1, right? But in the continuous time case, since this n was replaced with t and t is a continuous variable, we have this varying form. It is not going to be 1 everywhere, right? So we didn't have that distinction there in continuous time. But in discrete time, since this can only take integer number of values, you can see this e power 0 omega naught n in the e power n into 2 pi by n into n is going to be same, and they are not distinct. So it is not required to also have some a0 e power j0 omega naught n plus some terms plus an e power j n into 2 pi over n into n. This is not necessary, right? Because this everything can be combined and written as a0 plus an e power j0 omega naught n. This one single term is enough. So you either need to have this term or this term. And this is going to be true for all. So even if you take 1, so 1 omega naught and n plus 1 omega naught, and you have 2n plus 1 omega naught, and so on, everything it is going to be equal to same. So 2 omega naught you will have n plus 2 omega naught, 2n plus 2 omega naught, and so on. For 0 you had n omega naught, 2n omega naught, and so on. So to represent a function or signal in terms of this complex exponential, it is only enough to represent it over a period of n or over only n samples. So I'll represent it like this, which means the summation is over only n sample. It can start from anywhere, right? But it should only extend over n samples. So then what I have some coefficient, let's say ak, and I have e power j k omega naught n. And this omega naught is nothing but 2 pi over n, and n is your fundamental frequency.
Wow.
So I'm just hypothesizing. I can write my periodic signal in terms of complex exponential using this relation, right? Let's say this is an hypothesis. And if I'm able to find such a case, such that this equation holds true, then I can say this is a valid expression. Then the above expression is valid. So that will be my next step. So I will see if I'm able to find such a case such that this equation is possible. So what I'll do, since x of n is periodic, I'll write periodic with period n. So x of n is periodic with period n. So let me write it this way. x of 0, I can write it as k equal to n ak, because this term is going to be equal to 1. And x of 1 will be summation k equal to n ak e power j 2 pi by n into n. And I can write until x of n minus 1 summation k equal to n ak e power j n minus 1 into 2 pi by n into n. Sorry, we are actually substituting n, right? So this will be k. It is still in under the summation. So in this equation, we are only substituting n with 0, 1 and n minus 1. So what do I have here? So on the right hand side, I have ak's. How many are there? So 0, 1 to n. So n ak's are there in the summation, right? N unknowns. And how many equations are there? These are like linear equations, right? I again have n equations. And if I actually try to find out, these n equations will be linearly independent. Then I can have n solutions, right? I can get all the possible solution. I can find one solution, right? One solution having this, all the unknowns, I'll be able to find. So this proves that AKs exists and they are unique. Unique meaning there can be, for A0, there can be only one value for this given set of conditions, right? So then we can say this is also called as the discrete time Fourier series. So then I can say my DT Fourier series exists. But it is not always the case that you have to lay down these n equations and then try to solve and find out. There is a simple way. So before doing that, let us see what happens to the sum I'm just gonna write down. So sum n equal to n e power jk 2 pi over n into n. So we want to observe what happens to this. So first case we will take if this k is equal to, this is a multiple of n basically. So plus minus n, plus minus 2n and so on. So what happens? Then you will get it as summation n equal to e power j. So it is multiple of n. So we will get some m times n into 2 pi over n into n, where m is an integer. So this will be equal to summation n equal to n e power j. So you'll have 2 pi, n cancels, m into n. So this is nothing but the integer multiple of 2 pi, which we already saw it is going to be 1, right? And it is summed over n terms. So this is going to be equal to n. So when k is a multiple of n, our summation is going to be equal to n. Let us see what happens when k is not a multiple. So k is 1 if otherwise, or k is not a multiple of n. So then what do we have? Summation. Let's consider one interval. So 0 to n minus 1 e power j k 2 pi over n into n. So this is like a finite GP, right? GP series in which we have summation n equal to 0 to n minus 1. A power n will give me, or AR power n will give me AR power n minus 1 by R minus 1, right? This of course. So here what I have, A is actually 1 and my R is e power jk 2 pi over n. So what will my sum be? It will be 1 into e power j k 2 pi over n into n minus 1 by e power j k 2 pi over n minus 1. So this is going to give me e power n cancels j 2 pi k minus 1 by e power j k 2 pi over n minus 1. So this term is equal to 1 for me. This is equal to 1. So 1 minus 1 will give me 0. So for all other case which is not a multiple of n, my summation is going to be equal to 0. So let me note it down. So this is equal to n for k equal to plus 0, plus minus n and so on, and it's equal to 0 otherwise. So this result we'll use and try to find out our a case from this equation. So we have x of n is equal to summation k equal to sum over n ak e power jk into 2 pi over n into n. So let us multiply both sides by e power minus jr into 2 pi over n into n, let's say, and sum over n for n terms. Okay, so I'll have sum equal to n x of n e power minus jr 2 pi over n into n, and on the right hand side I'll be having, I already have sum over k ak e power jk 2 pi over n into n, and I'll have additional e power minus jr 2 pi over n into n, and summation r equal to n. Okay, so now right hand side what I'll do, I'll invert the summations. So I'll take k terms on the outside. So in this I have only ak, and let me combine these both, since this is again sum over n, right? We are summing over n. So n terms is here, so I should keep them inside. So e power j, I'll get k minus r into 2 pi over n into n, right? And we already know this summation is equal to n for k equal to r, or k minus r is a multiple of n, right? 0 plus minus n and so on, or 0 otherwise. And let's say I'm restricting my k and r to less than n, 0 to n, then only possibility is my k is equal to r, right? So I'll get summation k equal to n ak delta of k into r, right? Which means that only that it exists only for k equal to r. All other case it is going to be equal to 0. So my only term that will come out of this summation, because now I am going to vary k, is that ar, right? Because all other terms, this is going to make it 0. So this is equal to 1 if k equal to r, 0 otherwise. Okay, so only my ar term will survive. And what is my ar? The summation n equal to n x of n e power minus jr into 2 pi over n into n. And let me replace r with k. X of n e power minus jk 2 pi over n into n. And I also missed this n here, right? So this will be n. This will be n ar. So this is going to be 1 by n. So this is equal to 1 by n. So this is my closed form expression of a case. Okay. And this is called as my analysis equation. And we had the original Fourier series equation, right? So x of n is summation k equal to over n ak e power jk into 2 pi over n into n. So this is my synthesis equation. So this we already know, because we are synthesizing x of n using a case, and here we are analyzing the AK, which is nothing but the Fourier series coefficient. So AK is also called as the Fourier series coefficient. And this is also called as the spectral component or spectral coefficients of x of n. Why? Because it says the decomposition, or it governs the decomposition of x of n into sum of harmonically related complex exponentials. So we can say n harmonically related complex exponentials. So all these e power j k 2 pi by n into n, with this k varying from 0 to n minus 1, are harmonically related. That's what it means. So from the analysis equation, we can also see that your ak is also periodic. So ak plus 1 is nothing but 1 by n summation n equal to n x of n e power minus j k. K you have to replace with k plus n, right? 2 pi over n into n. So now this you can write it as e power minus jk into 2 pi over n into n plus this 2 pi n, right? And this is equal to e power minus jk 2 pi over n into n. So this is equal to ak itself. So your AKs are also periodic with fundamental period n. Okay. So again, similar to the continuous time case, you can see the similarities. So your x of n, you have e power plus jk 2 pi n over n into n, and while ak you have this 1 over n terms, n term, and also you have minus jk. Okay. So again, let us try to see a simple example. Let's say my x of n is sine omega naught n. This I can directly decompose into the complex coefficients. So I'll have e power j omega naught n minus e power minus j omega naught n small n by 2j, right? And if I write my omega naught equal to 2 pi over n, this is nothing but 1 over 2j e power j 2 pi over n into n minus 1 over 2j e power minus j 2 pi over n into n. So what are my coefficients? This is a1 because I have a coefficient 1, and here I have a coefficient minus 1. So my a1 is equal to 1 over 2j, and by a minus 1 is equal to minus 1 over 2j. And if I, let's say for example, if I take n equal to 4, then my AKs are also periodic with n equal to 4. So my A 5 also will be equal to 1 by 2j. It is also equal to A9 equal to A13 and so on, right? Similarly, I have A minus 1 equal to A3 equal to A7 equal to and so on equal to minus 1 over 2j. So if I try to plot it versus k, what will I have? Let's say 0, 1, 2, 3, 4, 5, 6, 7, minus 1, minus 2, minus 3, minus 4, minus 5. So at 1 I have 1 over 2j, and minus 1 I have minus 1 over 2j. So then I am going to repeat it every 4. So 1 over 2j, and this side 1, 2, 3, 4, minus 3 it will be 1 over 2j. And here 1, 2, 3, 4 at 3 minus 1 over 2j. And at 7 minus 1 over 2j. And here again at minus 5 it is minus 1 over 2j. So this is how you find the Fourier series coefficients. So if it is some other difficult to find straightforward, then you have to use this expression A case to find the A case, the analysis equation. And again in the discrete continuous time case, we had something called as the Gibbs phenomenon. Right? But here, since our discrete time Fourier transform is actually, Fourier series is actually sum of finite terms, which is n, right? The periodic. So we don't have such convergence issues. So once you have all the n terms, it is going to definitely converge. So there is nothing like continuity not continuous in the discrete time domain, right? So we don't have any convergence issues here. So now let us look at the properties of the discrete time Fourier series. So again, most of the properties are similar to its continuous time counterpart. Still, we'll go ahead. The first property is the linearity. So for convenience, let me state the Fourier transform like this. X of n Fourier series gives AK. Okay. So linearity, what I have? If I have x1 of n having Fourier series AK and x2 of n having Fourier series BK, then if I take some ax1 of n plus bx2 of n, then my Fourier series will be aak plus bbk, and of course both x1 of n and x2 of n are periodic with same period, with period n. Okay. So the proof is pretty straightforward. So from the first line we can get x1 of n is equal to summation k over n ak e per jk 2 pi over n into n, and your x2 of n is nothing but summation k equal to n bk e per jk 2 pi over n into n. Since the period is same, we have written only n here. And here, if you add this ax1 of n plus bx2 of n, then you will have a into summation k over n ak e power j k 2 pi over n into n plus b into summation k equal to n bk e power j k 2 pi over n into n. So you can combine this, take the summation common. You will have aak plus bbk e power jk 2 pi over n into n. So this is your Fourier series coefficients. Okay. So the second property is the time shifting property. So time shifting, you know, it doesn't change the period, correct? So if you have x of n giving Fourier series coefficients ak, what do you think x of n minus n naught will give me? So let us take a look. So x of n, what do you have? Summation k equal to n ak e power j k 2 pi over n into n. So I'll write x of n minus n naught. So summation k equal to n ak. This n alone I need to replace with n minus n naught. So now I can write this as summation k equal to n ak e power minus jk 2 pi n naught over n, 2 pi by n into n naught e power jk 2 pi over n into n. So this is like the Fourier series coefficient of x of n minus n naught, because these are all similar, correct? So it will be ak e power minus jk 2 pi over n into n naught. So it is just like a phase shift in the Fourier series domain. So next let us see what happens if we do frequency shifting. So frequency shifting. So let's say my x of n gives, I've written fs, right? ak. And what will come here if my Fourier series is ak e power k minus n, what will come here? That I have to find out. So we can either use the analysis equation or the synthesis equation. So I think the analysis equation will be straightforward. So we have ak equal to 1 by n summation k equal to n x of n, this n, right? So e power minus jk 2 pi over n into n. So k minus m, you have to replace k with k minus m. X of n e power minus j k minus m into 2 pi over n into n. So then this is nothing but 1 by n summation n equal to n. So this will be x of n e power j m into 2 pi over n into n. And then you have the normal minus jk 2 pi over n into n. So this is what is my desired thing. So this will be x of n e power j m into 2 pi over n into n. So if I have this signal, then I'll get my Fourier series coefficient as ak minus m. I'll get something like a frequency shift. So fourth, let us look into conjugation. So if my x of n gives ak, what does my x conjugate of n give me? So let us see. So x of n, what do I have? Again, ak e power jk 2 pi over n into n. So if I take a conjugate, I'll get k equal to n ak star e power minus jk into 2 pi over n into n. So I need to replace k with minus k. Summation, let me say k equal l equal to minus k or k equal to minus l. Then I'll have my l again. If I have it from 0 to n minus 1, it will be going from 0 to minus n of minus 1. But this again, the summation is still over n terms only. So I'll still have n. Here I'll have a minus l star e power j l 2 pi over n into n. Now I can replace l with k. So x star of n is equal to summation k over n a minus k star e power jk into 2 pi over n into n. So my Fourier series coefficient of x conjugate of n is a minus k conjugate. So I have reversal in frequency and also a conjugate. So next let us look at time reversal. So we'll be doing a similar thing. So x of n equal to, so gives me Fourier series ak. And what about x of minus n? So what do you think from this derivation? It is simpler, right? So if you have minus n, only this n will become minus. So this form will be similar, but here you will have ak. So at last you will get a minus k. So that is the only difference. So we'll derive that also. So x of n is nothing but summation k equal to n ak e power j k 2 pi over n into n, and x of minus n is nothing but summation k equal to n ak e power minus jk into 2 pi over n into n, and replace k with minus k. So here x of minus n is nothing but summation k over n a minus k e power jk 2 pi over n into n. So this here thing is a minus k. Okay. So now let us look at time scaling. And we'll look at expansion in time domain. Compression, anyway, you are guaranteed to miss some of the sequence, right? So if you have this thing, if you compress, they are going to go in between, and those signals will get, those sequence or series will get lost, right? Those samples will get lost. So we'll only consider time expansions. So x of n, if it gives ak, what about x of n by m? And again, this n by m need not be an integer. So what we'll do, we'll consider some signal like this. So this is equal to x of n by m if n is multiple of m or 0 otherwise. For example, if you have 0 and 1, minus 1, this is x of n, and then your x of 2n will be, for 0 it is 0, for 1, since 1 by 2 is not an integer, it will be 0, and at 2 it will be 1, and same as minus 2. So this is what they mean here. So if this is our signal expression, then what will this give me? So that we have to find. So let us write, let's say ak bar. So this is going to be periodic with period mn, because if this is periodic with period n, x of n by m will be periodic with period mn. Okay, so then I will have 1 by mn summation n equal to period of mn, right? And then I will have x m of n e power j k 2 pi over mn into n, right? I have to sum over this for n. But if you know your x m of n is equal to x by n by m for n equal to some, let's say some rn, correct? R into m, right? So all other case it will be equal to 0 otherwise. So what I can do, ak prime is equal to 1 by mn summation. So I can collect only those terms. So it will be true for x of 0, x of r, right? When I substitute n equal to rm, until x of n minus 1, correct? Let's say if I am considering the summation from 0 to mn minus 1, then only these terms will be non-zero. So I can write r equal to 0 to n minus 1, x of r e power jk 2 pi by mn into n is nothing but rm. So this I can cancel. So I can write it as 1 by mn summation r equal to 0 to n, which is nothing but sum over n, x of r e power j k 2 pi over n into r. So now this I can separate this as 1 by m into 1 by n. So this is nothing but my ak, correct, for x of n. So this x of ak bar is going to be 1 by m into ak, and its periodicity is going to be mn. So it is equal to 1 by m into ak. But ak itself has periodicity of n. So this 1 by m ak is actually going to repeat itself for m more times, and it is having 1 by m factor. So that is the expression we get for time scaling. So next property, let us see for periodic convolution. So for actual signal, we saw convolution being, so x of n convolved with h of n is nothing but summation k equal to minus infinity to infinity x of k h of n minus k. So this is convolution sum, or let's say just convolution. So periodic convolution, you're just going to perform it over a period. So I'll call it x of n, and I'll use this notation. H of n is equal to summation k over n, or I can take some other variable r, okay, it doesn't matter. So k over n, x of k, h of n minus k. So this is periodic convolution definition. So let us see if we take two signals. So x of n gives me Fourier series ak, and if h of n gives me Fourier series coefficient bk, what happens to the periodic convolution? I'll define r here for convenience. So this is actually going to give me n into ak into bk. So let us see that now. So let me call it, what should I call this as? So let's say some pk. So then what will I have? I'll have summation k equal to k over a period of n, right? Or in other words, I'll have 1 by n, n equal to n, and I'll have this term, summation r equal to n, x of r, h of n minus r, this into your e power minus j, here it is k into 2 pi over n into n. So now what I will do, I will first sum n and then sum r. So then what I will get? So I'll have 1 by n, summation r over n, and xr I can take out, and then I have summation n equal to n, h of n minus r, e power minus jk into 2 pi over n into n. So I will replace n minus r with some integer m. So n is equal to m plus r. So what will I get? pk equal to 1 by n summation r over n, x of r, and the summation will be m equal to n. So it will just shift by r units, but still the number of terms will be n. So it doesn't matter for us, right? Since we are considering over any of the n periods, n samples. So it doesn't matter if it is starting from 0 or r, doesn't matter for us. Okay. So then h of n minus r I will replace with m, e power minus jk to 2 pi over n, and I'll have m plus r here. Again, my summation is just over m, so r I can take it out. So 1 by n summation r equal to n, x of r, e power minus jk 2 pi over n into r, and I have summation m equal to n, h of m, e power minus jk into 2 pi over n into m. So this is nothing but my bk into n. So 1 by n will give me bk. So this will be n into bk. And what is this? Okay, first let me write this down. E power minus jk 2 pi over n into r into n bk. So this is constant. I can take it outside. So then I will be left with bk into summation r over n, x of k, e power minus jk to 2 pi over, this is x of r, sorry, 2 pi over n into r, right? So this is nothing but my n into ak. correct? So then this total is going to be n into ak into bk. So this is what we said first. Okay, this is the proof for the periodic convolution. So next let us see the multiplication property. Multiplication. So multiplication, let's say x of n, I have Fourier series of ak, and my y of n I have Fourier series of bk. I need to find out what is my Fourier series coefficient for x of n into y of n. So from the first thing we can see x of n is equal to summation k equal to n ak e power jk into 2 pi over n into n, and my y of n I can use a different coefficient, let's say r equal to n ar e power jr into 2 pi over n into n. So if you multiply these two, so I will get this into this. So summation k equal to n ak e power jk 2 pi over n into n. Similarly, summation r equal to n. This is br, right? So br e power jr 2 pi over n into n. And I need to get it in some form of summation, let's say L equal to L over n, some dk e power j dl, dl d j power L into 2 pi over n into n. So I'll get n into n terms. So n square terms I'll get, and I have to group them to get it of this form. For example, suppose I want to get the term of d0, I should look for the coefficient of e power j0 into 2 pi over n into n, which is nothing but the constant term 1. So when will this happen? If I have e power j 0 into 2 pi over n into n into e power j 0 into 2 pi over n into n, or e power j 2 pi over n into n 1 into, and e power j, if I have n minus 1 into 2 pi over n into n, then also this will give me 2 pi factor, and this will be equal to 1. Or I should have 2 e power j 2 into 2 pi over n into n into e power j n minus 2 into 2 pi over n into n. Or in general I should have e power j k into 2 pi over n into n and e power j n minus k into 2 pi over n into n. So in terms of coefficients, what I'll get? I'll get ak into b n minus k, right? And b n minus k, I can also write it as ak into b minus k. This is for d0, right? I will get summation over k, this term. So if I want d1, what I should get? I should get summation over k, some ak b 1 minus k, such that when I multiply these both coefficient, I should get 1, right? So I'll get something like this. So similarly for d, let's say L, what I'll get? Summation k, ak b L minus k. So this is my general term. So that is what I want here. So my dk will be nothing but summation al b k minus L, summation over L. And how much? Over 1 period. This just over 1 period. So here I have written in terms of L, K, here also I'll write in terms of L. Then it will be simpler. Or maybe I'll change it there, so it is easy for you to understand. So here I'll have dl, dk. Okay. Fine. This is the property for multiplication. So next property, let us look at first difference. So this is nothing but x of n gives ak. First difference is x of n minus x of n minus 1. So this you already know. For x of n minus 1, you are going to get you will just have ak into some phase term, which is nothing but e power minus j 2 pi over n into k. Your n naught is nothing but 1 here. So what will this be? This will be 1 minus e power minus j k into 2 pi over n into ak. So this will be your first difference. This is similar to differentiation in your continuous time domain. And next, let us look at running sum. This is similar to your integration. So you have x of n giving Fourier series coefficient ak. What about summation k equal to minus infinity to sum n x of k? So what will be its Fourier series? So to see this, let us assume y of n equal to summation k equal to minus infinity to n x of k. And also this means that your a0 is equal to 0. Otherwise this sum itself will not converge, correct? Because you're summing from minus infinity. So let us see what happens to y of n minus y of n minus 1. So this is nothing but your summation n minus summation over n minus 1. So it will give me x of n itself. So now if I take Fourier series on both sides, let me call yk it is some bk. So I'll get bk into, this is the first difference, 1 minus e power minus jk 2 pi over n, right? And what will be my xk? Xk it is ak. So my bk is nothing but ak over 1 minus e power minus jk into 2 pi over n. So it is just my, like here it is multiplication in the first difference. The running sum, it is going to be a division. So bk is what I'm interested in, right? The Fourier series coefficient of y of n. So this is ak by 1 minus e power minus jk 2 pi over n. And if you see at k equal to 0, this is going to be, the denominator is going to go to 0 itself. So you should also mention this is for k not equal to 0, comma a0 equal to 0. Otherwise the spectral component at 0 will be infinite. So next we have the Parseval's relation. For discrete time periodic signals. So Parseval's relation, we know it relates the energy in the time domain to energy in the spectral components. So let us see, let us say x of n has a Fourier series ak, then we can say 1 by n summation n over n and x of n mod square is gonna be equal to summation k over n ak mod square. So this is nothing but like an average power. So average power in x of n is equal to the average power in the spectral components of x of n. So that is what this Parseval's theorem states. So let us look at the derivation. So we need to get something of x of n mod square. So what we do? We first consider this multiplication. So x star of n, x conjugate of 1, what is the Fourier series? The same minus k, right? So multiplication, we already have the property. So it is going to be dl equal to summation k over n ak into bl minus k. So we have dl equal to summation k over n. We have ak into b, here is b, and we have, what did we have? L minus k, correct? So let's go this way. B k is a minus k. So b l minus k is nothing but, you have to replace k with l minus k. So it will be a into minus l minus k. So it is going to be a k minus l. Okay, so it will be a k minus l here. So this is what we have for dl. Now if we write it in terms of the synthesis equation, we have x of n into x conjugate of n equal to So synthesis equation, we have summation. Here let's say L equal to n dl e power jl 2 pi over n into n. Now we need to get this side, this thing, right? So I do summation 1 over n, summation n equal to n, x of n, x star of n. So this side also it will be same, 1 over n, summation n equal to n. And we have summation L over n, dl e power jl 2 pi over n into n. So left hand side I have got what is required, right hand side I have to simplify. So this is mod x of n whole square. And if I take this summation n inside, what will I get? L equal to n, dl summation n equal to n, e power jl into 2 pi over n into n. So now this summation is equal to n for L equal to 0, correct? Or plus minus n and so on. And is equal to 0 otherwise. So I'll consider only L equal to 0 because the sum itself is over any period of n. I'll take L equal to 0 for convenience. So what will I be left with? L equal to 0 to n minus 1 dl n into delta L. Delta L is, this is equal to 1 if L equal to 0, 0 otherwise. So in this summation only my d0 term will survive. So I'll get d0 by n into n. So it will be d0. So what is my d0 here? Just I have to substitute L equal to 0. So that is nothing but summation k over n ak into ak, which is nothing but summation k over n ak is, sorry, again this is ak minus star, right? A minus k conjugate. So this is also conjugate here. So I missed that. So that's why we did not get the mod ak square. So now we'll get the mod ak square. Okay. So this is the derivation. So that's all for the properties of Fourier series of discrete time Fourier series. So it may look quite daunting at first time, but it is all derived from two simple equations, which is nothing but the analysis and the synthesis equation, right? So where did we have this? Here. So everything is derived from only these two equations. All are consequences of this. So initially you can try to derive them and you can solve some questions based on them. And once you are used to it, it will come naturally for you. You don't have to memorize or muck up anything, okay? But please go ahead and try to derive them. Only then you will be able to understand. So even in future, if you forget, you will be easily able to quickly derive them and you can remember for a further long time. Okay guys, so that's it for today. I'll meet you in the next lecture. Until then, take care. Bye-bye.